Hello and welcome to Toddcast number 54. This is going to be focused completely on something known as the Grignard reaction, which is a reaction that will convert a carbonyl, aldehyde ketone, or a carbonyl leaving group such as an ester into an alcohol. And it does so by adding a carbon to the pre-existing carbon chain. And so just for what it's worth, a Nobel Prize winning and very, very powerful reaction that was done in 1912 was when he won the Nobel Prize, which means this chemistry probably goes back to the 1800s, but it was a game changer. Biggest thing they had to do is build carbon-carbon bonds, make longer carbon-based molecules, which was a huge breakthrough in engineering, medicines, plastics, just all sorts of compounds. So rather than go in the history of it, just want to go into then the details of it. So as mentioned, it starts with a carbonyl. I'm going to choose a ketone to begin with, but again, this could be an H, or it could be a leaving group such as an OR, an anhydride, a whole bunch of different options that we'll look at. But when there's no leaving group, when it's just two R groups and neither of them are very good at leaving, then it'll undergo what's known as a carbonyl addition reaction. So I'm going to start with essentially the same template every time. So I want you to line up molecules, make your life easier. But MgBr carries a overall plus charge, so +2 for magnesium, -1 for bromine. So overall +1, it forms a more of a polar covalent than a true covalent bond between carbon and magnesium. But it gives carbon negative. And so these electrons in this carbon-magnesium bond are loosely held on magnesium. So carbon can take them and attack a carbonyl, which it does. Forms a fifth bond to carbon, which means the weakest bond, which is the pi bond, breaks. And as we've seen with reduction, when you add that fourth atom to this carbon, you now generate a negative on the O, and then the MgBr, the 2 plus and -1 of the bromine combines for a plus. So that plus aligns with the O. There's no leaving group, so if the negative were to kick back in, it can't kick out an R group, an R group, or an R group. So it ends up, it just has to stop at that point, just carry out addition. So you're going to add an R group to this carbon of the carbonyl and an H to the oxygen of the carbonyl. And so this will come out and pick up an H. And again, you'll notice this template looks identical to the reduction ones we did because guess what? Reactions, behavior carbon is pretty consistent. So whether it's an H minus from an AlH4 minus, or whether it's an R from an MgBr R, you're going to get the same sort of pathway. R is going to attack, add to the carbon, O is going to get protonated, and you're going to with an addition reaction. So note that you form a tertiary alcohol and a ketone, which makes sense because you had 1, 2 R groups. I have 1, 2, 3 R groups. Okay, so that should make sense. But note that you increase number of carbon bonds by 1, and you convert a carbonyl, in this case a ketone, into an alcohol. Okay, if we have a leaving group, the rules are a little bit different. So without a leaving group, it does an addition reaction. With a leaving group, it's going to do a substitution reaction, not an SN1 or SN2, but a carbonyl substitution, where it's going to go on and eventually kick out this OR leaving group. So same starting template. Going to put the MgBr in the exact same orientation, except now we have an OR and ester leaving group. It's going to attack, and you end up with almost an identical looking intermediate. You have the O minus stabilized by the MgBr plus. You have 2 Rs, the one that you had originally and the one you just added. But instead of like up here, we have 2 Rs, you now have, or 2 original Rs plus a new third R, you have the original R, the R you added, and now you have an OR, which is a good leaving group. So if these electrons come in to form a fourth bond, or a fifth bond to carbon, I should say, it'll kick out that OR leaving group. So they come in, they kick out that OR. Now with a ketone, plus this OR minus, but the OR minus isn't going to really do much of anything. It's going to be a conjugate that's going to float around the solution. But what you end up with is a ketone, which is exactly what the Grignard reacted with up here. So now we know Grignard reacts with a ketone. In fact, because of resonance with this donating in, again, this is a little less electrophilic because of the resonance donation from O. It's a smaller delta plus than you'd have with a ketone. So for the exact same reasons that lithium aluminum hydride reacts with this and sodium borohydride does not. We now have a situation where Grignard, if it can react with a ketone, it can definitely react with an ester. Ester is more, less reactive. So if it, I should say, if it attacks an ester, it definitely can attack a ketone. So it adds once to form the ketone, but then it can add a second time. Basically, we're going to carry out the exact same thing we did from here. It's going to be repeated here. So notice this is essentially the same intermediate, except the two R groups weren't the original two. Now these two R groups are the ones we added, and the third one is the original one. Once again, you still get a tertiary alcohol. But we added 2 plus 1 for the Grignard. We ended with 3. We added plus 1 plus another 1 for 3. So here we start with 2, we add 1 through an addition reaction. We have 3 R groups on the carbon, so we have a tertiary alcohol. Here we only had 1 R. The OR is a separate entity, it's a leaving group. So we had 1 R, we added 1 to make a ketone, and 1 more to make the tertiary alcohol. Okay, hopefully that seems reasonable. So after everything, we have our tertiary alcohol up here, our tertiary alcohol here, and although they look similar, this is the result of 2 identical things being added. These 2 do not necessarily have to be the same R group, so you could end up with a chiral center if you had 2 different R groups and the one you're adding is yet a third one. Whereas here, you're always going to get 2 identical R groups because it adds the same Grignard reagent twice. Okay, so let's consider what the Grignard reagent is doing. It's acting as a nucleophile and attacking the carbonyl. And so if you recall, a nucleophile is a Lewis base, an electrophile is a Lewis acid. And so because RMGBr attacks carbonyl to form a new CC bond, it is, as mentioned, a Lewis base or a nucleophile. So we can get rid of choices A and B. Those are just wrong. What happened along the way, and we maybe didn't even notice it, was we went from 2 bonds to O to 1 bond to O. We lost a bond to O, which we now know is reduction. Gain of O is oxidation, loss of O is reduction. So without even realizing it, we carried out a redox reaction, which means a Grignard reagent is causing reduction, causing the carbonyl to get reduced. So it is acting as a reducing agent. You'll note it is connected to a magnesium, which is a less electronegative atom, and it finishes bonded to a carbon, which is an equally electronegative atom. So it lost a bond to a less electronegative atom. So its oxidation state goes up by 1. Okay, so just definitions, terminology. I want to summarize what we'll see then. So first thing you need to do is identify the Grignard reagent, MGBr. You can also see it as MgCl. I'm kind of stuck on MGBr just because that's I out of laziness did the same reagent over and over and over. But it could be an MgCl as well. This C minus is going to attack the carbonyl. We have to decide leaving group. Ethyl groups, R group, not going to leave. H is not going to leave. So we end up getting an addition reaction. So with an aldehyde, it undergoes addition, meaning it adds just once, and you form the alcohol. So 1 R group on here, the ethyl, plus 1 new R group, in this case the methyl, result in an alcohol with a ethyl, a methyl, and then the H, ethyl, methyl, and H. You'll notice that you get both the S and the R alcohols. So 50-50 mixture, so no optical rotation. This time we're going to do a ketone. I'm going to start with a ketone that's symmetric on both sides, so I don't have to worry about stereochemistry. But just as with the aldehyde, R and R, no leaving group. So it's going to undergo addition reaction and just add once. So this time I have 2 bonds to R, so 2 R's if you will, and I'm adding a third R, this methyl. So it's going to finish as a tertiary alcohol. So 1 carbon bond here, 1 carbon there, third one there. No chirality, so no concerns with R and S. And then we have now a leaving group. It looks weird, but the leaving group, even although it's part of the same molecule, this bond here is an ester bond, so it can be broken. This is known as a lactone, which is a cyclic ester, so we'll say it's an ester. When you have a leaving group like an ester, it can add twice. So one can go on through a substitution where the ethyl group will go on and kick out the O, and the second one will go on and undergo addition. So your first one will displace the O leaving group. So there's my O leaving group. So if I label this O right here, that becomes this O right here after it leaves. This O here becomes this OH here. And we add one of these ethyls through substitution. We add the other one through addition across the carbonyl. So if I have no leaving group, it adds just once. If I have two, or I have a leaving group, it adds 2 times. So 1 + 1, aldehyde forms now secondary alcohol. 2 R's plus 1 more means ketones make tertiary alcohols. Esters or any compound with a leaving group will form 1 + 2 more tertiary alcohol as well. Okay, so let's see how we do. Summary-wise. So I'm going to stick with the same short chain just so it's easy to write. Want to point out, mentioned this real briefly in passing last time. I'm going to mention in passing this time every time it pops up. But this is known as a ketal protecting group. What is normally here, 2 bonds have the same O. So this would normally be a ketone, but it's protected so that the Grignard can only react at the aldehyde and not at the ketone. And so we'll go through that as a synthetic strategy. But whenever you have more than one type of functional group on a molecule and you only want to react with one of them, you sometimes have to protect the one you don't want to have react. You turn it into something else, carry it the direction you want, and then return it to the original state you had it in. Okay, so for this one, aldehyde, so my first thought should be it adds once. So when I have an aldehyde, the R prime Mg is going to come in, kick that up, so undergo an addition reaction, gets protonated, you need to work it up. Work up represents whatever you need to do to make it a neutral molecule. So if this is an O minus, then the workup would be mild acid. So mild acid might mean a protonated amine, like ammonium, methyl ammonium, something like that. Fairly common that you use a very mild acid like, I don't know, pK around 10 or so. You'll protonate it, and you end up with this. The problem if you use too strong of an acid, you end up getting E1 elimination, and you lose your alcohol and turn it into an alkene. So mild acid workup. Note that this one has H, R, R prime. As long as R prime is different than R, you're going to get a chiral center. So this one almost always gets a chiral center. So it adds once because there's no leaving group, and you go from 1 carbon to 2 carbons, you're guaranteed to have 3 different things at least. In all likelihood, you have a chiral center. Ketone. So for a ketone, same stories had in the previous examples. No leaving group, so it's going to add once. Again, mild acid workup. So this time I'll draw a compound. So I might do ammonium. So ammonium chloride, for instance. So ammonia with HCl will turn into ammonium chloride. Weak enough that it won't overprotonate it. It'll just make the alcohol without causing elimination. So no leaving group, adds once. 2 carbons go to 3. Possibly chiral. Notice I've changed the word. So probably, because high chance this one's going to be different than this other R. But with 3 R's, there's a higher chance that you're going to get a match. So for instance, if you drew cards, draw 2 cards, the chance of matching is low. Draw a 3rd card, and the chance of one of them matching the other one goes up with each time you draw a card. So 3 R's have a greater chance of having 2 match than 2 R's. Not all 3 match, but just getting at least 1 match. Okay, ester, we've done this as well. Has a leaving group. Note that it could also be an anhydride, which is an O with another carbonyl and an R, or an acid halide, such as an acid chloride with a Cl or acid bromide with a Br. As long as I have a leaving group, this can add twice. Once through substitution, where you get a ketone, and then to that ketone, it can add a second time. And so because you have a leaving group, it adds twice. So you end up going from 1 carbon to 3 carbons. You get a tertiary alcohol, and it can never be chiral because you add 2 identical groups. So because you had 2 identical groups, not chiral at all. Okay, so why do I care about this? Well, I cared because of a question like this. So which of the following is most likely to give you a chiral center? And so what I want to do is just make note of the fact that if you have an ester and an hydride, it adds twice. You're going to add this R group twice. If you add an R group twice, you do not have 4 different substituents. So, as mentioned, you decide if they add once or twice. To an ester, it adds twice, ketone once, anhydride twice, aldehyde once. So for the ester, it adds twice. You have 2 identical R primes, achiral, so that can't be true. And anhydride, same story. You end up with 2 identical, so it's achiral. So that one's also eliminated. So it's only the ones where it adds once, where it only goes in addition reaction, not substitution followed by addition. Ketone could be chiral because these might be different, these might be different. But aldehyde is the one that's more apt. So note that it says the most likely. You could have an aldehyde that you start with where you add the exact same R group. So if R equals R, and it's achiral, but in all likelihood, you'll get a chiral center here. This one, these two could be equal, or this could be equal to this one, this could be equal to that one. There's more cases where this will be equal. So same belabored point I was doing earlier. So I know for sure A and C are wrong, and I believe D to be a better answer than B. Doesn't mean B isn't possible, doesn't mean A or D, doesn't mean B is not possible, and it doesn't mean that D is always true, but it's a better answer, higher probability. Okay, this reaction, absolutely imperative that you know this. This is going to be our second way of making new carbon-carbon bonds. The first one we learned was to deprotonate an alkyne. That negative charge is a very good nucleophile, so it'll attack an alkyl halide, such as alkyl bromide or alkyl chloride, and add a triple bond with whatever R group is coming off of it. So that's definitely one way to add to an alkyl halide. But now we have a way to add to a carbonyl known as a Grignard reaction. So this is our second reaction for forming carbon-carbon bonds. And just like it was earth-shattering when it was discovered way back when, it is going to be really, really powerful for what you're doing nowadays, because it will change your synthesis options tenfold. Because I know how to oxidize an alcohol to a carbonyl, and I know how to take a carbonyl and add an R group, like through a Grignard reaction. So I have a whole new plethora of different reactions I can do. So with no further ado, I'll call this a lecture. Thank you for joining in, and I will see you at the next podcast. Bye.